Well, hello everybody. Here I want to show you a little experiment. Up to now we calculated the inertial forces and torques of the one-cylinder engine theoretically. But now I want to show you this theoretically works in practice. So we have a one-cylinder engine here, and when we want to measure the inertial forces that are acting on the frame. What have been the results for the balancing of the first harmonic? The summary of the lecture before. We see here the one-cylinder engine with a crankshaft, connecting rod and the piston. Here we see MA, this is the counterweight at the crankshaft for balancing the first harmonic. And here we have the result of the first harmonic in X, in Y and in X direction. We see in X direction we have Q1 times sinus phi plus the part of the counterweight. This is a reduced form by divided by L omega 1 square of the force. So these are masses. And here in X direction we have it with Q1 and Q3, and here we have the counterweight. And here we have three balancing situations. The balancing situation, we remember, we have longitudinal force balancing, transversal force balancing, and mean balancing. And for these different balancing, we have different balancing weights. For MA, once Q1 and Q3 to have a longitudinal force balancing. So in X direction 0, we have a remaining force in Y direction, or transverse direction. And in transverse force balancing, we have the mass only Q1. And we have a remaining force in X direction, and is in Y direction is 0. And for the mean balancing, we use Q1 and a half Q3. So we have remaining force in X and Y direction, but with a constant magnitude. And that's why we could balance it with another weight, but turning in the other direction, because after the mean balancing, the rotation of the force is not in the rotation direction of phi, but in the opposite direction, so it's rotate with minus phi, the force that is acting on the frame. And now what I would like to do, I would like to show you that this theoretical results are also, we can also see in practice. So we have here a one-cylinder engine. It is driven for the moment very slowly. This is coming from a lawn mower cutting grass. And this one-cylinder engine, we see here the rotating crankshaft, we see the connecting rod, and we see here in this case the piston. This one-cylinder engine is mounted on a plate, this plate here, and as you can see, if it is driven like this, phi is going in this direction, so we can describe also the Cartesian coordinate system such that this direction here is the positive X direction, like this, and this is the positive Y direction. We see it also written here on the plate, that this is the positive X and positive Y direction. We need it later for understanding the results. This one-cylinder engine is now driven by what? Not a combustion process. Here we see it's not possible, but underneath we have a motor. Let's show what it is for a motor, like this. We see here the motor, here in black. It's an electric motor with a power supply. And this motor is directly mounted on this plate. Directly mounted on the plate. This motor is not connected directly to the frame. And all these assembly, one-cylinder engine, motor, are mounted on this plate, and this plate is directly connected to the frame by this round iron bars. 1, 2, 3, and behind 4 iron bars are mounted. And each iron bar is provided with strain gauge. Here, you see it. This is the strain gauge, and by using the strain gauge and all this, with this little mathematics, you can compute from the strain the forces that are acting on the frame in X and in Y direction. So here we have the outcome of the force in X and the force in Y direction. What will we do with these signals? These signals are weak, so we have to amplify them. So here's a cable going directly up to this measurement equipment. And this measurement equipment here, we have here an amplifier, we have here a filter, and we have here a oscilloscope for showing the results. Again, from underneath here, the cable are going like this, and in behind of the amplifier. The amplifier amplifies the signal, and we have two signals, the X and the Y force. And these signals are then going into this filter. Why it's going into the filter? Because once we want to see the first harmonic and then the other harmonics. And after this filter is here, there are two signals going here in the oscilloscope. And this oscilloscope, you can see the results. What you say here is an X-Y coordinate system. So this is the X, that positive X direction, the positive Y direction. That you can see. In this point, we see the forces that are acting on the frame. You remember, you see here this X and Y force. These are shown here, what has happened here. To give you an idea that it is this here, the positive X direction, and this here, the positive Y direction, I make a little experiment. First I stop it. So no power supply, we have a still standing mechanism. And for the still standing mechanism, we have here the position nearby zero. I can adjust it a little, the point. Now it's again zero. Here you have possibilities to adjust the point. And what I do now, I will apply a force in this positive direction of X. So in this positive direction of X, I want to supply a force. I do it with my hand. So in this case, like this. And when I do it, you see then the force showing here it going in positive X direction. So when I apply here, I see my force that I apply in X direction, not in Y direction. And when I push my finger now in the positive Y direction, we should see the results here in the oscilloscope. So this is the positive force in Y direction. And so if there are forces acting on the frame, so if there are forces here acting on the frame, we measure them and then we can show them on the oscilloscope. What I didn't mention up to now is the power supply of the motor. You see underneath the black motor, and then the black and red cable here to the power supply. And when I have 2 voltage and 1 ampere, we have this. And when I give here a little bit more power, you will see that now the machine is quicker. Okay, so you see that the machine works. And while it's working, we would like to see the results. And the result you can see here, quite nice. You have this kind of Easter egg here. I can say it here a little bit more. This more for 5 seconds. So in this case, this is the pulsograph of the force that are acting on the frame if it's turning with this velocity. Okay. I do it again like this. So here you see it. And what you see a little bit, that the points are going in the direction of phi. You know, it's like this, that this is going in this direction, so you have a rotation in this direction of phi.
What I can do now is to change the filter in order that I put more filter in it, so I want to have only the first harmonic. All higher harmonics are gone. And you see what happens.
Now our ellipse one, that is the pulsograph of the first harmonic, because I filtered the higher harmonics and they are not responsible for this signal. Only the first harmonics. And you see the rotation goes in the direction of phi here. Very nice, in the direction of phi. And we have a nice ellipse one. Okay, it's not really directly, but I have to remember also for the signals that if now I take also the second harmonic for the signals, that we have not what we have to consider. We have clearance. There's not the exact X direction in the piston direction. So there are some uncertainties and tolerances to consider. We have friction and all this. Okay. But will the friction be seen by the forces in X and Y? No. But the friction may cause of vibrations. And the vibrations will change a little bit the signal here underneath. But here it is quite nice. The first result that we see here in this case, and when I make the amplifier, first now I want to change it here like this. So we see the first harmonic, the clear first harmonic. So we have this result without this counterweight. Now we have here 3 different ways, and we need 3 different counterweights. We need Q1, Q3, and a half of Q3. And yeah, we have these masses here. This is the mass Q1. Hello Q1, I'm Q1 for eliminating the transverse force. And this is Q3. This is Q3 for cancelling the first longitudinal force together with Q1. And this is the half of Q3. And what I would like to do now, I want to make the same. Here, in this case, we have longitudinal force balancing. So, what will happen? We will have here only in Y direction result, and in X direction nothing. So it will be not a circle, but it will be something like a line here in Y direction. So what I do is here, I stop the power supply, and then for the longitudinal force balancing I need Q1 and Q3. So Q1 and Q3 are here. These masses I put here at the counterweight side. Here are certain things to put here. So in this case, up and down, I put Q1 and Q3. So here we have at this position Q1 and here Q3. I'm look if it's rotating. Yes. And now I give them the power to have at about the same speed than before. And if we look now for the signals, we see, wow, it's really great. I have only a signal here. I have only a single in X direction. In Y direction, excuse me. So the X direction is completely gone. Now the idea is to put away, to have also higher harmonics. So the filter I put away, and then you see this, that if you take under, if you consider also higher harmonics, then you have something like this, a curve like a moon. This we can understand by adding the second harmonic as we did in the last lecture. Well, now we're going to do the transversal force balancing. Here we need only Q1, not Q3. And then I have no force in Y direction but in X direction. What I have to do now, because here is Q1 and Q3, I have to leave Q3. I have to leave. Oh, so only Q1 is here. And now I put the power. I see this is a rotation with only MA times LA by L1 is equal to Q1. So this. And now we see here the result like this, that we have not a really line, but nearly by. But we have a lot of clearance, so it's not clear, but I have to put the filter to see only the first harmonic, no higher harmonics. And if it's like this, it's going to show, yeah, we see our first harmonic of Y. We see also that this first harmonic is smaller than the ellipse one. The length from, the length from here to here must be equal to Q3. Wow. So now I can stop, and now I can want to make a mean balancing. For the mean balancing, I need to counterweight M1, Q1 plus the half of Q3. This was Q3. Now, please, hey, this is the half of Q3. The half of Q3 I put on the counterweight side. It turns. I put on, and I'm looking for the story. What must be happen that we will see a kind of circle for the result. And if we look here, we see, wow, it's a kind of circle. And if you look a little bit clearly, you see that this circle is rotating in the opposite direction of phi. Again, the rotational is like this of phi. But here, if you see clearly, a little bit more clearly, you see that it's rotating in the opposite direction of phi. Exactly as we found out. And if we change now the filter such that in this case the filter is, we have also higher harmonics, you see the circle is changed a little bit, especially at the borders. Here it's nearly good, but here and here, because of clearance and other things, we have artifacts, and so it is not really as we probably would found out if we make a computational model, or if we compute the forces up to the fourth harmonics. Well, that was a little bit experiment with the one-cylinder engine underneath here, and here you see a little bit the arrangement of the measurement. We will have it also on the slides, and we can all what we found out before, we can prove it in an experiment. And I think this is very nice, because now you see that you have a strategy in order to make minimum a balancing of the first harmonics. Thank you for listening to this experiment.